So we got a lot to do today. So we're going to do next assessment at the end of class today. It'll be on the stuff we're currently doing. So engaged, thinking caps on today. Here we go. So this is just an overview of what we're doing. It's an overview. So remember we talked about this rate with exact rate of change. What is our goal? Our goal is exact either net accumulation or total accumulation. So this is the rate of change of oil entering the ocean, and this is the accumulated volume of oil in the ocean. And so this is, in general, it's the idea that you know how fast something is changing. You know how fast something is changing every moment, and you want to know how much you have at every moment. Okay? So we know that what the rate profile is. We want to recover the accumulation profile, whether that's net accumulation or total accumulation. Okay? And then we saw that the key to doing this, the key to getting accumulation from rate is constant rate of change, right? Because with constant rate of change, so given a rate, what? We can calculate a little bit of accumulation as long as that rate is constant. Remember that? As long as that rate m is constant, then we can say a little change in volume is m times whatever little change in time we have. And then we could also, given now that we calculated a little change in volume, we know that some new value of volume is an old one plus the change. So here's this idea, you know how fast something's changing every moment. So given a constant rate, we can get a little bit of accumulation, and then we can calculate a net or total accumulation. So what's the key to all this? Constant rate of change is the key. Without constant rate of change, we can't do these calculations to do accumulation. All right. So we were looking at, so last time in class we looked at just one little interval, right? We took a little change in time and we looked at that interval and how we could create the accumulated volume of oil in that little time. And then we said, well, if we did it this way, it would take forever, right? Because how many little changes in time is there from 0 to 2 days? Like millions, right? Or thousands at least. Okay? So we said, let's instead on the right slide here. What just happened? Yeah, so we said let's instead let's break it up into big intervals, right? We'll break up the time frame into big intervals, and then we'll have constant rates, right? We'll have constant rates in each interval according to the exact rate at the left side of that interval. That's kind of where we left it off last time, right? Okay, and then we wrote down what that rate function was. So we call that approximate rate function R. Okay, so the real rate function is the red one, and then we got this approximate rate function R. And why, if we have the real rate function that's exact, why do we want this very poor approximation of R sub b? Why do we want this very poor? Because it, why? Yeah, right. And what is it about this that makes it possible now? Right. Okay, so now we're able to actually find amounts of accumulation. And what is it about that approximate rate function that lets us do that? Right. So the whole deal is our approximate rate function is based on constant rates. Constant rates will allow us to actually generate little amounts of accumulation, like I just showed you on the previous slide. So let's just, so this is the new function created from RV that approximates the function RV. In this case, with these big intervals, it doesn't approximate it very well. But the idea is there, right? The blue one's trying to be like the red one, but made up of constant rates, right? Okay, so I want you to, I'll zoom in on this. So let's just practice here. So I've got to give you four values of the R function, the approximate rate function. And I want you to exactly and approximately write down what each of these is. So R of 0.5, how can you represent it exactly? And what is it approximately? And then R of 0.2, and then R of 0.9, etc. So work on these individually, and then if you want to talk it over, you can talk it over too. So think about it. How would you represent each of those rates of the R function, right? These are all going to be rates coming from the R, the blue R function. So represent those exactly and approximately. And I've got another, this is for your use, optional, if you want to write on this. When I say approximately, I'm saying, what is that value approximately? I'm not talking about the fact that we're approximating the red graph with the blue graph. It's not that. It's just estimating, like an estimate for R of 0.5. Value. An estimate. It's not referring to the fact that we're approximating one function with the other. Okay. All right, how we do? So R of 0.5. He wants R sub v of 0.4. Lots of yeses in agreement. Okay? And then that is approximately equal to what? 17. All right, so R of 0.2. R sub v of 0. It's 28. Okay, what about R of 0.26? Andrea, what's R of 0.26?
R of 0.26 would be, oh golly, we don't have that. Oh wait, no, 0.26, sorry, not 2.6. That would be R sub v of 0, and that would be approximately 28.
Okay, and what about R of 0.39? Kelly. Same thing. Every value from 0 to 0.4 in days has the same value of R, which is R sub v of 0, right? Because we're using, for that whole interval, we use the real rate, the actual rate at the beginning, and then that becomes the approximate rate for that whole constant for that whole interval, okay? Got a picture of that? Okay, and so then we said, any questions? So then we wanted to write this function. And so, am I using a different interval than last time? We're going to go with today's, whatever today's is. Okay, so we're going to use R sub v of 0. And that's from 0 to all right, and where should it be equal and not equal? Equal to 0, not equal to 0.4? Is that what I said last time? Okay, and then R sub v of, actually last time I said equal, anyway, so R sub v of what? In the next interval is from 0.4 to, sorry, is this 0.5? Sorry, 0.5.
No, it's 0.4.
You're right, sorry. So from 0.4 to 0.8. And so actually last time I put the equal here. Should it be on the left or on the right? Oh, so yeah, yes, exactly. If we were going with the way it's the images here, then it should be closed on the left. If we're just following exactly what this image shows. All right, and that's R sub v of 4, and then R sub v of 0.8 from what? 2, 2, 2. Is there one more? There's one more. We'll just do the first 4. Okay, that's fine. So now what we want to do is we've got constant rates, right? We've got constant rates, and we know from constant rates, we know all the mathematics that we need to build up accumulation. So we're going to do that. We want to write out what's going on here. Okay, so we want to write the accumulation function based on, this is 1.2. Okay, so we're going to write the accumulation function based on these constant rates. Based on these constant rates, so we know the math, right? So we're doing a function now, so we want to think about any point. So if we increase at a constant rate, what was the accumulation at 0? So what's the total accumulation at 0 days? 28, right? The total accumulation at 0 days is 28. Is that right? No? Well, lots of you said yes, so I was going to go with that. 28? Initial accumulation at time day 0. Not 28, right? That's the rate of change. That's the rate of change. So what did we say it was? Yeah, we said it was 0. The net accumulation and the total accumulation is going to be the same because there's no ocean, there's no oil in the ocean at time 0. So we're start here at 0, and we're going to increase at this constant rate of 28. We're going to increase at this constant rate of 28. So generally, what will our accumulation function look like at the beginning? What's that? So she's a slope of 28, meaning, what does the graph look like? Steep line. A steep line. Okay, it'll be linear. So if we think of any point on that line, think of any point on that line at x days, and what y is a of x, can we write then what the rule will be to represent any point on that initial line? Can you write the rule for any point on that initial line, meaning the final accumulation starting from 0, what's the final amount of accumulation, given a rate of change of, and all we had to do now is just use r of x because we've already defined all the right rates and the right intervals, right? So given the rate r of x in this first interval, which is r v of 0, can you write out the rule for every correspondence point between 0 and 0.4 for the accumulated oil in the ocean? Applying what we've done several times. Can you do it? Okay, go for it. So this is going to be from 0 to 0.4. So again, we want the amount of accumulation for any value x in this first interval. Any value of x days in the first interval, how much oil has accumulated? So think of that as like y final. You're finding y final for any x, right? Any x. Okay, so Rachel, tell me.
We said it was r sub v of 0 or 28 times x.
Okay, and how did you arrive at that? Okay, so yeah, you want to pick it up from there?
So our y initial is 0.
Y initial is 0. Okay, so
Then you have 0 plus v of y.
0 plus the change in y. Okay.
And then the change in y is the rate times d of x, basically.
Right. Rate times change in x. Good.
Okay, so the rate is rv of 0.
Okay, but we let's go ahead and use this now, right? So what is the rate? Just
So r of x.
r of x, right? Which in this interval will give us rv of 0. Okay.
And then the change in x will be from the final x to x.
So okay.
0, which is 0. Alright, so it's just x.
X. Right, just x because it's x minus 0, right?
That was the most complicated explanation that I just thought of. I was just gonna be like, this, and then I just went to zeros. Because you thought I was at zeros, and I was like, no, for that interval, it's.
Okay, do we agree on that? Yeah, so yeah, if you have r of x times x, it's correct. But can you justify it? So as long as you can justify why that's correct, that's okay. Here we're like just deliberately using, even though there's lots of zeros, deliberately using this idea of y initial plus the change in y, and that change in y is the rate times the change in x, and that rate comes from our rate function that we've already defined over here, right? In that interval, Rx is R sub v of 0. All right, so next interval. Karen, can you tell me in the next interval, so now we're going to go from 0.4 to? Uh-huh. Can you tell me what it'll be? Yeah, the accumulation in this next interval.
I want to say it's r of 0.4 plus r of x parentheses x minus 1.
Here's what Karen's offered up. Is this right? Is this what you said? What do you think? Sophia?
Instead of r of 0.4, wouldn't it be a of 0.4?
So she's suggesting a of 0.4 instead of r of 0.4. I have a yes, I have a no.
I can explain where I got that from.
Yeah, go ahead.
So basically, like we've set the rate constant from 0 to 0.4 kind of thing. So we have that one. To start for our next interval, we need to start from where we left off in our last interval.
Right.
So we've accumulated up to 0.4.
Okay.
So that's our new y initial.
Okay.
Accumulation of up to 0.4.
So you She wants to change. Karen agrees. Yes? A? Question.
A of 0.4 is what we're defining now.
Right?
So that's not going to return anything.
Yeah, what's going to happen when we tell this function a of 0.4? Where's it going to look? Oh, it's going to be on the right side. So do you see now why we've got to put the equals on the right? So that we can call the function, we can call all the accumulation from the last intervals. You see? So yeah, it feels like, since we're defining it from the left, that it should be closed on the left, closed circle, and then open on the right. But in order to define that accumulation recursively like this, that we're always gathering all the accumulation from the previous interval, we really need all the equals to be on the right sides. And then so in this first one, both will be equal, but then after that, we're going to do what we call open on the right and open on the left and closed on the right, meaning equal on the right. And then that allows us to use this recursive idea that all the accumulation up to that point is now we get from the previous command, previous line of the function, and it works. Wow. So good catch. Okay, and then the rest, once we got the pattern, the rest is easy. You just write it down. So now we're going to take all the accumulation up to 0.8 and add the change in accumulation in this interval, which will be the rate times. Etc.
For that first one, do you want to use an equal sign?
Yes, right. So in the first one, we'll do both because we need 0 to be defined somewhere. Okay, so is this just finding, say this one right here, is it just finding the accumulation at the end of the interval? Is it just finding the accumulation at the end of the interval at, say, 0.8? Or something else? So this interval is from 0.4 to 0.8. Is what I put a cloud around, does that just find the accumulation at x equals 0.8, or does it find something else? You're saying it finds all of them in between? Yes? Yeah, because x varies, right? X varies from 0.4 to 0.8. And as x varies, dx varies, right? This is dx. It varies. The rate stays constant. But yeah, x varies through the interval, and then dx varies likewise, x minus 0.4. And so as a function, it gives us every amount of accumulation from 0.4 to 0.8. Not just start plus the whole change gives you the end. By letting x vary, then we generate every correspondence point in that interval. Does that make sense? The beauty of a function, right? The beauty of a function. One formula can give you all this information, all those dependent values or amounts of volume in this case. Okay, so then in order to sketch it, though, to help us sketch it, we might just find the points at the end of each interval, and then we just connect the dots. But knowing that each of these lines, let's do that. So how much accumulation do we have at 0.4? So we got a calculator handy? How much accumulation do we have at 0.4? Yeah, lots of you have GC handy, right? The best calculator there is. So anyway, what is 11.2? So when we get to 0.4, we're at 11.2, something like right here. But that line that we wrote, Rx times x, gives us all these points in between. Whoa, missed. One more try. Wow. My thing is angled differently than I expected it to be. All right, and then how will we find at 0.8? How do we find the total amount of accumulation at 0.8? We take the 11.2 and add what? Everyone do it. Where is it? Just tell me tell me the process. Where are you getting that number 6.8, and what does it mean?
I took the difference between 0.8 and 0.4,
Okay.
and then I multiplied it by r sub 0.4,
Okay.
because that's the rate of between 0.4 and 0.8.
Okay. And you got
6.2.
0.4 times, I guess, 17.
Yeah, 0.4 times 17.
All right. And so should I add here at point A? Should I go to 6.8 then?
No, you should add 6.8 to 11.2.
Okay. Can you do that and tell me what you get?
18.
18 at 8. Sorry, 0.8. Okay. Am I in the right line? Something like that. It's not my finest line day. There we go. Etc. Right? So, but then by drawing that line, we're drawing all those correspondence points in that interval, according to the x changing to that interval, and likewise dx, right? So that cloud there represents arbitrary point dx, which is x minus 0.4. And then what dy or dv is rx times dx. Okay, any questions on making the accumulation function? Yeah?
Rather than rx, wouldn't it be like r.4, because the rate at that between those 2 points is r.4?
Okay, so is it r.4 or I have rx? What do you guys think?
Rx, because you already defined that one.
Yeah, so what is rx between 0.4 and 0.8? How do we define rx between 0.4 and 0.8? You're looking in the wrong place. How do we define rx between 0.4 and 0.8?
Rx between 0.4 and 0.8.
You're looking in the wrong place. Now you're looking in the wrong place. Okay. Here's where we defined rx, right?
Oh, right.
So what is rx between 0.4 and 0.8?
It's r sub 0.4.
Right. So it's already defined. So that's the nice thing about now through this whole ax function, we can just write down rx, because all the rates will be right according to what we've already defined them in the right intervals, right?
Oh, okay.
You see?
Yeah.
So we're in that interval 0.4 to 0.8. What is rx? It's r sub 8.4.
Oh, so it is r sub 0.4, but it's just written in a different way.
Right. Yeah.
Okay, I get it. Thank you.
Yeah, sure. Okay. Other questions on this? Okay, let me show you what the next GC file is. We'll do a week from today. Let me show you what it is.
Do we have anything you want to say?
No. But everything you can start working on before Thursday, or you can take a break. Okay, so this is oil slick part 2. All right, this is oil slick part 2. Here's how this works. So there's the same rate of change function, and then I'm graphing that from 0 to 30, but we're just going to show from 0 to 3. Yeah. Okay, so you're just going to have your window show from 0 to 3. And then what n does, n is the number of intervals that you're going to have between 0 and 3. So right now n is set to 1. So there's just one interval from 0 to 3 that's going to have a constant rate. We're going to use the left side. So this is an interval of 3 for a constant rate trying to be like that function, right? Really bad. But if you move n to be 2, then it will split up 3 into 2 intervals, and you'll have 2 constant rates approximating r sub v. etc. So here's n equals 3, n equals 4, and you see what happens as you change n, you get a different accumulation graph over here on the right. And I'm just showing the different colors in the accumulation graph just to emphasize the fact that those are still straight line segments, right? This is a piecewise linear function, just like the one we just built. Because then so you want R to be as much as up to 10. So this is now from 0 to 3 with 10 intervals, and then the resulting accumulation graph.
Do you want ours to be different colors like that too?
Not a huge important. I mean, so you can choose. You can make it different or the same. But I'm putting it different just to show you these are still even. So when the number of intervals starts increasing, it's going to look more like a curve, but it's really still not a curve, right? Even with 1,000 intervals, it would look to your eye would look just like a curve, but it's 1,000 little straight lines, right? So, but less important. If you want to have fun with color combinations, go for it. Okay, so here's kind of the ground rules. This rate function, you're going to do it in one command line. Okay, part of that command line to graph this blue approximate rate function is this. It has this in the command line, so it's using this technique that we've seen before. A is a number of 1 to up to 10. So it's going to be up to you to figure out what is the value of A representing. What's the value of A representing? And how is that helping you graph this rate function with the variable n in one command line? Now, the piecewise accumulation function will require a separate function for each piece. I tried to make it work with one command line, like one piecewise. It doesn't work. For some reason, it doesn't work. So, but the rate you can do, the rate you can get in one line, but then you're going to find a different function for each one of those linear pieces, and then graph that. And then so you define the function and graph it for each one of the pieces in the accumulation function. Okay, so just so you know, this makes it a little bit easier. At any given point, when you actually always graph. Okay, so let's figure out a way. All right, so with the accumulation graph, even though you show the right number of intervals from 0 to 3, it can still be graphing all the rest out here outside of 3, okay? So that you don't have to, just by displaying from 0 to 3, you'll see the right number of pieces, but you can, to make it easier, you can always just have it display all 10 pieces, no matter what the value of n is. Okay, so when n is small, here n is 2. So from 0 to 3, you're going to see 2 pieces, but you're still going to have all 10 pieces going way out to whatever it goes way out to. So that just makes it a little bit easier on you. Okay, the rate function, pretty easy to only show the ones you want to show from 0 to 3. That shouldn't be too tough. Okay, questions on this assignment? Initial questions. You can refer to the video and see this again. But changing n, change the number of intervals from 0 to 3. And then part of your command line for the that R function is going to be A is a member of 1 to 10. 1, 2, 3, all the way up to 10. So you have to figure out how n and A mathematically fit into graphing this R function, right? So R sub v is actually the red function. So I've already graphed the red one up here. You're figuring out how in one command line you can graph this blue step function. So the piecewise accumulation function, you'll have a definition for every piece and a line graphing each piece. We want to do that as efficiently as possible, okay? So if things start to blow up and get crazy, then we'll want to rethink how you're doing it. Any questions on the design? Yeah. So if n is 2, so n is 3. So for the rate graph, it just only shows those 3. But just to make it easier on you, you don't have to only show 3 based on, that would be kind of tricky to do that. So you can just graph all 10 every time. Does that make sense? And then you're just going to show, but you just would be, if you're using it, say didactically, you could just leave it showing 0 to 3, and you would never see those other ones. Does that make sense? Having this cut off, because you're doing it as 10 separate functions, having this cut off at 3, maybe it would be easy, I don't know, but you don't have to. This n will be how many intervals there will be from 0 to 3. Okay. Yep. So if n is 8, see how long it takes me to get to. I don't understand that question. Well, for the rate of change, you're just displaying the new function from 0 to 3. Okay. The approximate rate. Okay. I guess I could have done that here too. The accumulation you want to show from 0 to 3. But to make it easier, you can just always graph all 10. Even the ones that go beyond 3. That will just make it easier on you. It's not a requirement. The whole point is we're just only going to, if we use this for teaching, for conversation, we'd only show from 0 to 3. Okay? We would never look on beyond 3. We would just change on. But for building the animation, it's okay if there's stuff out beyond 3. Okay? That's what I'm saying. If that makes it easier. Other questions? Okay. So let's do this. So you can, that'll be in the video. Reference that. Show you an animation. You're going to answer questions based on animation. Spread out your tables. Okay, so here's the animation, explanation. Values of function f give the volume of concrete being added to the floor of a New York skyscraper during a 45-second pour. Values of the function r sub f, defined as this function, give the rate of change of f in meter cubed per second at each moment of x, 0 to 45. So this is highlighting the interval from 5.2 to 6 seconds.